Decision properties of context-free language. So why we need these decision properties? So these are used to conclude whether the given problem, okay, we have a problem. So using these properties we can conclude whether the given problem is decidable or undecidable. So when can we say that a problem is decidable? So if there is any solution, okay, so if we are able to find solution or if we are able to construct any algorithm for the problem, we say that that problem is decidable problem. Example, so if I ask you to find even numbers between 0 and 200, you can write an algorithm for this, right? So these type of problems, it comes under decidable problems. Whereas coming to undecidable, there is no solution for a problem. So if there is no solution or if we are unable to construct an algorithm for the problem, then they comes under undecidable problems. Example, sometimes some problems or some programs they may go into infinite loop. So without providing any output, such type of problems they comes under undecidable problems. So what is the main aim of decision properties? They are used to find whether the given problem is decidable or not. Now let us see the properties. Here we have three properties. First one is emptyness problem. Second one is finiteness problem. Third one is membership problem. So all these three problems are decidable problems. Along with this we have one more called equivalence problem, which is undecidable problem. So we'll discuss about these three decidable problems in our lectures. So first let us see about this emptyness problem. What is emptyness problem? Here we'll check whether the given, here check whether or check if the grammar generates empty language or not. Okay, so say suppose we have language like this, there is nothing inside, this is an empty language. So you need to check whether the given grammar generates this empty language or not, and the steps involved in this are, so you need to check whether start symbol contains useless symbols, start symbol or start production, or start symbol contains useless symbols. If this is the case, then it will definitely generate empty language. Okay, so in order to avoid this, you need to remove useless symbols from the grammar. Okay, so what is emptyness problem? Here we'll check if the given grammar generates empty language. When grammar generates empty language, if start symbol or start production generates or contains useless symbols, then it generates empty language. So in order to avoid this, what we need to do, we need to remove useless symbols from the grammar. So let us see some examples about this. Say suppose we have a production like this. Okay, there is no A production or B production or C production. Okay, we have just single production and you can't generate string of terminals from this, right? So how can we write this? S derives AB and this again S derives BC. Okay, from A we can't generate anything, from B nothing. Again it's same in this case also. Okay, so as we are unable to generate string of terminals in this case, we consider these symbols as useless symbols. Okay, the start symbol contains useless symbols. So obviously we don't get any string of terminals here. So obviously language generated by this is empty. Okay, this is the example for empty language. As we are unable to generate strings from the given production. Next, we'll see one more example. So, let it be one more grammar. Now, check this grammar if this grammar contains any useless symbols. So here A S derives AB. Okay. So from A we have A. So you can terminate this A. Whereas from B there is no terminal symbol. So this can't be terminated because B generates BB. Again this B generates BB and so on. It just repeatedly B's will be generated, but we can't generate any terminal symbols from B. So this production is a useless production. And check if B is existing in the starting production. Yes, B is there in the starting production. As it is associated with A, this complete AB becomes useless. Okay, so now this grammar generates empty language. Okay, even though A is generating or producing terminal, as we are unable to produce terminals from the non-terminal associated with this A, this language or this grammar generates empty language. So then what is so we'll take one more example which is not an empty language. So let S derives AB, A derives some BC, then B derives CC by B, C derives A or B. Say suppose we have some grammar like this, then here we need to check again for useless symbols. So see this start with S derives AB, A derives BC. This B can be terminated with this terminal symbol B, whereas C contains again terminal symbol A. Here B is generating B. So we can generate string of terminals here. What is the string generated? BAB. So language is not empty now. So this is the example for non-empty languages. Okay, non-empty grammar. So this is about emptyness problem. So let us just revise this. What is the step 1? You need to check whether start symbol contains any useless productions. If it contains useless productions, then definitely that grammar will generate empty language. Whereas if it does not contain any empty language, then it will generate some set of strings. Okay, how to avoid this problem? So we can remove this useless symbols from the given grammar. If they are associated with the terminal present in the start production, then that definitely produces empty language. Next, second problem is finiteness problem. Second one. So here we'll check whether the grammar produces finite language or not. Check if grammar produces or generates finite language. You already know difference between finite and infinite languages, right? Okay, finite language. So we have few steps here. First we'll see the steps and then we'll go to example. Step 1 is first check if the given CFG is in CNF or not. Okay, Chomsky normal form. And step 2, say suppose if the grammar is not in CNF, then you need to convert it into CNF by using simplification process, eliminating useless symbols, then null productions, useless productions, and then unit productions. And we have few steps for solving or for converting the grammar into CFG. Use them and convert the given grammar into CNF. Once the grammar is in CNF, then draw graph for this grammar. Okay. Next, you need to, so now we have this graph. Check if graph contains, any loops or cycles. Okay, if this is the case, say suppose if your graph has loops or cycles, then we say that this is infinite language. Okay, if there are no loops or cycles, then that is a finite language. So these are the three main steps we follow in order to solve this finiteness problem. What is step 1? Check if the CFG or if the given grammar is in CNF or not. If yes, you can directly proceed with remaining two steps. If not, convert it into CNF by using the steps of CNF. Next, step 2 is draw graph for the obtained grammar. Next, step 3 is check if the graph contains loops or cycles. If so, then that grammar definitely generates infinite language. If not, if there are no loops or cycles in the graph, then it generates finite language. So let us solve one problem. So you just make note of these things so that while solving it will be easy. Okay. So let us take one grammar, the grammar which we considered before. S derives AB, then A derives same BC, then B derives CC by B, C derives small a by some small b. Take this grammar. What is step 1? Check if this given grammar is following rules of CNF or not. So what are the rules of CNF? Any non-terminal can produce non-terminals, two non-terminals, maximum two non-terminals in the RHS side. So you cannot have more than 2. Okay, this is one rule. And non-terminal can produce terminal symbol. Fine. So here if you observe, you have two non-terminals in the RHS side. So this is fine. Again two non-terminals, correct. Two non-terminals, then terminal symbol, terminals. So this grammar is in CNF. So no need to convert this again into CNF. So step 1 is over. You can directly start with step 2. What is step 2? You need to construct a graph for this grammar. So let us construct graph for this. So take 4 variables. S, A, B, C. Okay. Now draw this. S derives AB. So S derives A and B. A derives BC. A derives B and C. B derives CC. So you can write it like this. B derives C. So no need to write anything for this terminal signals. So this is the graph which we got. Okay. So now, okay, check if this graph is having any loops or cycles. So there are no loops in this. Okay. So as this graph is not having any loops or cycles, this is it is a finite problem and it generates finite language. If a grammar generates finite language, then we can find out rank for every node or every variable in the graph. So how to find the rank? So rank of a variable can be defined as length of the longest path from that variable. Length of longest path from that variable. So this is rank of the variable. Okay. So if you consider the C, so if you want to find rank of this variable C, how to find this? You need to calculate length of the longest path from this variable. So you need to check outgoing edges from this C. So as there are no outgoing edges from the C, rank of this will be 0. Okay. So how to find rank? You need to check if there are any outgoing edges from this node. So there are no outgoing edges from C, so rank of C will be 0. Now check this B. So from B there is an outgoing edge to C. Anything else? No. It has only one path, that is B to C. So rank of B will be 1. Now move to A. So what are the directions of A? Outgoing edges. One is A to B, B to C. Right? A to B, B to C. Second path is directly from A to C. So here you must take longest path. So longest path is 2. So rank of this will be 2. Now come to this S. So find out paths for S. S to B, B to C. Okay, one path is S to B, then B to C. Second path, S to A to B and B to C. S to A to B, B to C. So take longest path. Longest path is this one, right? So rank of this will be 3. This is how you need to find rank. So rank of the variable can be calculated only for the finite languages. Okay. So this is the main point you should remember in this finiteness problem.